oxygenation responses of the vastus lateralis muscles during maximum fatigue and intermittent cycling by Kieran Ashby. The aim of this study was to show the effect fatigue has on oxygenation in the vastus lateralis during maximum exhaustive exercise. Maximum exhaustive exercise we chose was HIIT, high intensity interval training. This is short bursts of maximal exercise followed by short, low intensity rest periods. Present findings show that oxygenation uptake fuels muscles in preparation for force production during sprint stages, although the uptake happens during recovery. Another way to put it is that tissue oxygenation efficiency uptake decreases as workload increases. This was found by Buchel. Our hypothesis: increased oxygen usage through the sprint stages by the vastus lateralis will directly help cause the presence of fatigue during cycling in participants' dominant leg only. This study was designed to show a difference/relationship between muscle oxygenation and muscle fatigue in dominant legs. The participants were first asked to find 14 centimeters above the lateral patella on the vastus lateralis and shave the area. Then they hooked up a NIRS system, that is a near-infrared spectroscopy system. It emits light on one optode, and then another optode picks up that light and reflects back readings on what it sees. Participants completed the test on a combined cycle called a watt bike. You can see on the right hand side testing procedure for all participants. Firstly, they were hooked up to the NIRS system, polar heart rate monitor to monitor heart rate during the test, and then they sat on the watt bike. Warm-up 1 consisted of 2 minutes at 75 watts, followed by a 2-minute rest. The rest periods were designed to get back any lost stores of energy through ATP and glycogen stores back into the muscles. Warm-up 2 was 3 minutes at 150 watts, followed by again 2 minutes rest. There was then 8 sprints that went for 10 seconds each, with a 20-second recovery in between each sprint. During this recovery, all data from the watt bike was given to Excel. At the end of the test, the NRS and the polar heart rate data was transferred to Excel. All data was collected and reported using mean and standard deviation. Houston's correlations were used to determine the relationship between our fatigue measures of peak power, peak cadence and distance, and our variables, sprint and recovery. The upper level was set at P being less than 0.05, and all statistical analysis was done using Microsoft Excel. Results: peak power relating to muscle fatigue changed throughout tests from sprint 1 to 8 by 41% in all participants, with a standard deviation of 15.4. Muscle oxygenation from sprint 1 to sprint 8 also changed around 5%, from 55.3 with a standard deviation of 11.6 in sprint 1 to 49.5 with a standard deviation of 14.1 in sprint 8. Likewise, recovery oxygenation for the dominant leg during sprints 1 to 8 changed 2%, 52.5 with a standard deviation of 14.9 versus 50.7 with a standard deviation of 14.1. Results during the sprints variable showed that Pearson's correlations performed on sprint tissue oxygenation and peak power was a slight moderate correlation of R equals minus 0.58, with P being greater than 0.5. Distance, a decline, and tissue oxygenation during sprints was also a moderate negative correlation of R equals minus 5.50 and P was greater than 0.5. During the recovery phases, tissue oxygenation on the dominant leg versus distance decline, again moderate negative correlation of 0.48, and again P equals greater than 0.5. The recovery oxygenation and peak power correlation was the strongest correlation of the lot, where R was equal to minus 0.63, but P was still insignificant. Discussion. Tissue oxygenation decreases over 5% during the sprint stages. This is because the oxygen is being consumed by working muscles, whereas in the recovery stages, the difference between sprints 1 and 8 is less than 2% tissue oxygenation. This would be expected to be seen as muscles aren't working as hard, therefore more oxygen can be stored in the tissues. Fatigue measures. Peak power decreased up to 41% with standard deviation of 15.4. This just shows the importance of powerhouse fuels in the cell, such as ATP, CP, and glycogen. Once those stores are depleted, power is massively depleted. It was found by Bishop that working muscles at near maximum capacity incur a decline in force production because of the limitations in energy supply. A big variance in peak power may be due to the contrast in participants' age. Our age group mean was 31.3, which is quite a high mean for an age group on athletic performance. Fatigue measures on oxygenation during sprints showed moderate negative correlations between groups. So there's no evidence that fatigue caused oxygenation increases or decreases during sprints and recovery. Muscle oxyhemoglobin consumed increased during sprint phases. As talked about before, the consumption of oxygen is because the muscles are working harder. In turn, we'd see a relative amount of deoxygenation or deoxyhemoglobin because the muscles have taken the hemoglobin oxygen molecule and separated the oxygen molecule, leaving just hemoglobin. Discussion. Recovery. There was a medium correlation with all three fatigue measures for recovery, but this was not enough to show statistical significance. So recovery resting muscles have an increased amount of oxyhemoglobin because the tissues aren't contracting, and this causes a decrease in oxyhemoglobin because there is not as many molecules of hemoglobin detaching from oxygen, so there is a decrease in oxyhemoglobin. Interestingly, for our group, there was 8 participants, and left leg dominance was seen in all the participants. Left leg was 51.6% with a standard deviation of 0.53, and the right leg was only 48.4% of the power with a standard deviation of again 0.53. Now, the interesting thing about this is 75% of our participants reported being right-footed dominant. It was found by Gentry and co. that right leg dominant individuals show left leg domination in activities which require postural stabilization and strength. This is definitely a strength activity. Conclusion. We found that the consumption of oxyhemoglobin causes the relative amount of deoxyhemoglobin in the cells. Oxyhemoglobin increases during strenuous exercise to feed working muscles, whereas less consumption of oxygen during resting phases occurs, so tissue oxygenation is up during recovery. We also found that fatigue doesn't increase tissue oxygenation or doesn't decrease tissue oxygenation during sprints and recovery. Fatigue studies in the future could look at more direct muscle fatigue measures. We looked at peak power, distance, and peak cadence. Further studies in the future could look at more things like the effect of ATP out of the cell. Practical implications for our study. Our study allows coaches of power athletes or power athletes themselves to develop more fatigue resistance power programs. So we know that the ATP depletion and the hydrogen ions in power causes fatigue, so we can train more short stuff, causing us to increase our amount of ATP. Are there any questions on our study? These are a list of references we used during our presentation.